Welcome to The Explainer. Today, we're pulling back the curtain on the hidden science that powers, well, pretty much everything you do online: digital streaming.
So let's start with a question you've probably had while binge-watching your favorite show. How in the world does a massive 2-hour 4K movie get to your phone almost instantly? I mean, the raw files for that should be absolutely gigantic. So how does it actually work?
The answer isn't magic, not at all. It's the science of digitization. It all starts by taking our rich analog world, actual sound waves and light, and translating it into the only language our devices can understand, the simple binary code of ones and zeros.
Okay, let's dive into this. To really get how streaming works, we've got to look at the fundamental Lego blocks of any digital media file. And we're going to start with audio.
First up is something called the sample rate. See, when a microphone records sound, it's capturing a smooth, continuous analog wave. To make that digital, our devices take thousands of little snapshots, or samples of that wave every single second. For instance, CD-quality audio, that's 44,100 of these snapshots per second.
And this analogy just nails it. A low sample rate is like trying to draw a circle with, say, only 10 dots. It's going to look jagged and blocky, right? But a high sample rate gives you thousands upon thousands of dots, creating a much smoother and more accurate picture of the original sound. Okay, next up is bit depth. So if sample rate is how often we're taking a snapshot of the sound, bit depth is all about how much detail we capture in each one of those snapshots. It controls the dynamic range. That's the difference between the quietest whisper and the loudest explosion in a movie.
Think of it like a box of crayons. A low bit depth, like 8-bit, is the tiny box with just a few basic colors. Sure, you can draw the picture, but it won't be very detailed. But a higher bit depth, like 16-bit or 24-bit, is like having that giant box with every shade imaginable. It lets you capture a much richer and more nuanced recording. And the final piece of the audio puzzle is channels. Mono, super simple. One channel, one point of sound. Stereo uses two channels, a left and a right, and that's what gives your music that awesome, immersive sense of space. The only catch? Two channels means, you guessed it, twice the data. Now, let's switch gears to video, which has its own set of building blocks. Instead of sound waves, we're talking about a series of still images. Resolution tells you how much detail is packed into each image. That's your pixels. While frame rate tells you how many of those images flash by every second.
The whole idea of frame rate is really just like a classic flipbook. Each page is a frame. A low frame rate looks choppy and jerky, but as you increase the number of frames per second, or FPS, the motion becomes incredibly smooth. That's why movies usually go for 24 FPS for that cinematic feel, while video games are often aiming for 60 FPS or even higher for that super fluid action.
So, if more samples, more bits, and more frames always means better quality, why don't we just max everything out all the time? Well, that brings us to the central problem of all digital media, this constant tug-of-war between quality and file size.
The answer lies in a number called the bit rate. That's the total amount of data you need for every single second of media. And as you can see here, you figure it out by multiplying all those quality factors together, and that's when you discover the massive problem.
So let's actually run the numbers. We'll just use standard CD quality as our example. We take that sample rate, 44,100 Hz, multiply it by the 16-bit depth, and then multiply that by 2 for our stereo channels. The result is, well, it's staggering.
That is over 1.4 million bits for a single second of music. A 3-minute song would be over 10 megabytes. An uncompressed 4K movie, we're talking terabytes. This is completely impractical for streaming. It would take forever to download.
So clearly, sending all that raw data around just isn't going to work. The solution to this whole dilemma, the technology that makes Netflix and Spotify even possible, is compression. This is the secret sauce. This magic is done using special programs called codecs, which is short for coder-decoder. These are the engines working tirelessly in the background every single time you stream something. Their one job is to shrink the data down for its journey across the internet and then expand it back out for you to watch or listen to.
I love this analogy. Think of codecs as digital vacuum sealers. You take a huge, bulky pile of clothes, that's your uncompressed media file, and the codec just sucks all the unnecessary air out, shrinking it down to a fraction of its original size. Now it fits neatly in your suitcase, or in this case, your internet connection.
Now, codecs use two main strategies:
Lossless compression is like perfectly folding your clothes. No data is lost, and the original can be put back together perfectly. But for streaming, the real key is lossy compression. It's super clever. It permanently throws away data our eyes and ears are least likely to notice, like audio frequencies way too high for us to even hear, and that makes the file dramatically smaller.
And this is why we have different file formats for different jobs. A WAV file is uncompressed. It's perfect for professional audio editing where quality is everything. But for streaming, services like Apple Music use AAC, and Spotify uses something called OGG Vorbis. Both are lossy formats that find that perfect sweet spot between really good quality and a small, streamable file size.
Okay, so that's the science. But why does any of this matter when you're just trying to watch a cat video? Well, because it explains some of the most common and annoying experiences we all have online.
You know that dreaded buffering wheel? That spinning circle of doom? That is literally a race happening on your screen. It means your device just can't download the data, which is determined by the file's bitrate, as fast as it needs to play it. Your buffer, that little reserve of pre-downloaded data, has run out.
And this chart just drives the point home. It shows the massive difference in data needed for different things. A voice call needs very little bandwidth. Streaming music from Spotify is a bit more demanding. But look at video. Streaming high-definition video uses exponentially more data than anything else, all because of the immense amount of information that's packed into every single frame.
So if you remember anything from this explainer, let it be these key points. Higher quality always means a bigger file. Compression is the essential trade-off we make between amazing quality and real-world convenience. And it's that clever, lossy compression that truly makes our modern streaming world go round. And at the end of the day, it all comes down to bitrate.
This secret science is absolutely everywhere, from music production and video editing to game design and animation. Understanding these fundamentals doesn't just explain the world around you, it can actually empower you to create in it. So the final question is really for you to consider. Now that you know the rules of the game, how are you going to use them?